Friends, let us continue our discussion on chemical kinetics, and last time we saw several restrictions that come on the rate of reaction because of thermodynamic consideration. To recap what we saw last time, we said that if the reaction is reversible, then the rate of forward rate ratio of forward rate constant to backward rate constant is the equilibrium constant, and because of this we do not have freedom of choosing both forward rate constant and backward rate constant independently, because thermodynamics specifies for us what should be the equilibrium constant. So, if we choose any one of those constants, the other one is automatically fixed. The same applies to power law kinetics and the orders that we use with respect to forward reaction and reverse reaction. Let us continue this discussion further and see what happens when we have a reversible reaction taking place in a reactor, and to get a feel of how reaction rate changes as this reaction progresses, let us look at in qualitative terms. So, as we saw last time, we start with reaction summation nu j A j equal to 0 taking place in a closed isothermal constant pressure system, and let us say that this reaction is reversible reaction. So, what we have is forward rate backward rate. So, forward rate K f into product of C j raised to Q j product over all species. Similarly, backward rate K b into C j raised to Q j prime, and we also said last time that for law of mass action kinetics, Q j and Q j prime are linked to the stoichiometric coefficient nu j by these relations, that is Q j is half of mod nu j minus nu j and Q j prime is half of mod nu j plus nu j. Now, let us see how reaction rate varies as the reaction progresses. So, we have this rate of reaction which is forward rate minus backward rate, which is power law kinetics as expressed over here. Let us bring our definition of extent of reaction. So, C j is C j 0 nu j into alpha. Now, we have seen in the last class that these rate constants depend on the temperature, that is these rate constants K f and K b are functions of temperature. We see that concentration is a function of extent of reaction. So, concentration is a function of extent of reaction. So, now we have rate of reaction explicit function of extent of reaction and temperature, both forward reaction as well as reverse reaction. Now, what happens when the reaction takes place in a closed isothermal system or closed system? We have alpha, that is 0 at the start of the reaction, and it progressively increases. Now, in a non-isothermal system, temperature also can change. For an isothermal system, temperature is constant, but for non-isothermal system, temperature also can change. So, the question now we ask ourselves is what happens as reaction progresses. We are not worried about what reactor and so on, we will worry about it in the later half of this session. But just say that alpha changes and temperature also may change. So, depending on how alpha and temperature changes, the rate of reaction will change. Now, how alpha and temperature changes will depend on what reactor we are using, how we are operating and so on. At this moment, we are just considering for sake of illustration that alpha and temperature is varying. So, for different values of alpha, different values of temperature, how does the rate of reaction change? So, to see that, we see some rate contours here, but before we come to this, little bit of background. So, let us go back to our reaction, and we have our reaction summation nu j A j equal to 0, that is our reaction, and the exercise just now showed us that we can express R as R f of alpha and T minus R b of alpha and T. So, we have forward rate of reaction, backward reaction rate. Now, what we want to see is how this rate changes as alpha and T changes. Now, alpha and T are two variables. So, if we were to plot rate as a function of alpha and T, one would require a 3-dimensional representation, alpha on one axis, temperature on one axis and rate on another axis, let us say. That is little complicated. So, instead what we will do is we will try to see how the rate of reaction varies in a slightly different form. We will try to see the rate of these reaction contours, that is how, assuming that R is some constant value C, how does those contours look like in a phase plane of alpha and T. So, what we are going to see is a 2-dimensional representation. On one axis, y axis, we have alpha or extent of reaction, on x axis we have temperature, and so given a point we will try to see how does the rate of constant the contours of constant rate look like in this phase plane. So, what does it mean? It means that if I take all those values of alpha and T for which the rate has a constant value C, this becomes my contour, and join all those points, these become my contour for rate being constant. So, any combination of alpha and T on this contour all give rise to the same rate C. So, that is how we view this 3-dimensional picture into a convert this 3-dimensional picture into a 2-dimensional contour plot, and we are going to see this for variety of 2 different cases, when reaction is endothermic and when reaction is exothermic. Now, the background for this is as follows. So, what we are saying is we are going to see these contours for constant rate, and in order to see how these contours vary, let us also do one small exercise and take partial of rate with respect to temperature, and if you do this differentiation by plugging in power law kinetics into these two rate forms, we will end up with this particular form. I leave this to you, I leave this as a small exercise for you to do, but we get this particular form. What is E and E prime? E is we have a kinetic rate constant Kf, and which is Af e raised to minus Ef, or let us put, or E by RT, or to make matters clear, let us put subscripts F and B over here. So, Ef and Eb are the activation energies for forward and reverse reactions respectively. Now, it turns out that going back to our thermodynamics, we can also show that Ef minus Eb must be the heat of reaction delta H or enthalpy change. Now, this is additional constant posed by thermodynamics. That is, you have heat of reaction, you have activation energies for forward and reverse reaction or backward reaction rate reactions, and their difference must be delta H. So, now let us go and have a look at how these contours look like, first starting with when delta H is greater than 0, or in other words we are looking at endothermic reaction. Okay. We are looking at endothermic reaction. Now, first let us look at how these rate contours look like, and then we will come back to this to see why these rate contours look something like this. What we see here on the y axis is the extent of reaction, okay, alpha and temperature. We jumped the gun and went to exothermic reaction, but let us first complete with endothermic reaction and then go to exothermic reaction. So, first let us try to see what does these contours are showing us. So, what these different colored things that you are seeing is actually the contours for constant rate. Recall that we are looking at R equal to constant, okay, and what are those values of constant is shown in this color slide which is on the right hand side. So, brown for example denotes very high rates of reactions, and as I keep saying time and again, the numbers do not matter at this moment, but qualitative information is what we are interested in. So, the rate, that is this constant C, is decreasing as we are moving down this color slide from brown to dark blue. So, now let us try to see what these contours are. The first contour that we can construct is the simplest one, which says that R is 0. What is R is 0? R is 0 when the reaction has reached equilibrium, and that contour is shown in this violet color line, that is the topmost line over here, and which is a contour for R equal to 0, that is our equilibrium line. Now, what does it say for endothermic reaction? We have already seen this in our earlier class, that as temperature increases, the equilibrium extent of reaction increases, and this is that particular plot. Now, for any other value of C, we see that as extent of reaction increases, or at a constant extent of reaction, as we increase the temperature, the reaction rate is increasing. That is, if you let us say we just draw a horizontal line at alpha equal to 0.2, then as our temperature is increasing, this is a point where reaction rate is 0. So, that is the equilibrium condition, but as our temperature is increasing along this line, we see that we are traveling from the color region which is the dark blue to brown through various different transitions. That means the reaction rate is increasing. Now, why is this reaction rate increasing? That is, recall that what we are seeing here is at a constant value of alpha, as we are increasing the temperature, the reaction rate goes on increasing. Now, to see why this is happening, let us go back to our previous exercise that we did, and we said that for endothermic reaction, EF minus EB, which must be the heat of reaction, is positive. That means, EF is greater than EB. So, now let us consider a scenario where we started the reaction with alpha equal to 0 or with a low value of alpha. Now, initially you expect that RF, forward reaction rate, will be higher than reverse reaction rate. and EF is also higher than EB, okay, because reaction is endothermic. What it means is del R del T, this is understood that this is at a constant value of alpha, is always positive, because del R del T is a difference of two terms. The first term is always higher than the second term. Why? Because EF is higher than EB prime and RF is higher than RB, and as a result we have this particular result that del R del T is higher, always greater than 0. In other words, for a given value of alpha, for endothermic reaction, del R del T is greater than 0. And what does that mean in terms of these contours? For a given value of alpha, as we are increasing temperature, as delta T is positive, del R is also positive. That means the reaction rate will continuously increase, and this is what happens when you have endothermic reactions. That is, recall, all along we are saying that alpha and T, for sake of this illustration, we are changing them independent of each other. However, that is not always the case, because in a reactor there will be a certain relationship between how extent of reaction changes as temperature, or its variation is linked to the variation of temperature. So, we have to worry about that link, but we will come to that in a minute. Let us go to the exothermic reaction, and for exothermic reaction we see a different scenario. What different scenario are we referring to? If you look at these contours, for example, this contour is always monotonic, okay, all these contours are monotonic. Now, let us go to the exothermic reaction. Once again we see that we are seeing R equal to constant contours, starting with R equal to 0, which is this violet line. And recall, for exothermic reaction, the equilibrium extent of reaction decreases as temperature increases, and naturally this is that contour. Once again our color scheme is same. We have dark brown, which represents high reaction rates, to dark blue, which represent lower reaction rate. Let us go back and write this particular relationship which we saw earlier. Okay. Now, let us see what happens when you have exothermic reaction. So, let me once again take the same approach of horizontal travel on given value of alpha. Now, what do we see here? Notice the color change, okay, and that will tell you what is happening to the rate of reaction. What is happening here? Low reaction rates. Reaction rates are increasing as we are traveling along this. The color is changing from dark blue to light blue. That means the reaction rates are increasing. Then beyond certain point, the reaction rate, now notice the change in color from light green to the dark light blue to the dark blue. That means the reaction rates are once again decreasing once again decreasing in this range. So, what happened here? In this range, as we increase the temperatures, the reaction rates increased, but it started decreasing once again. That means, there must be a point where the reaction rate is maximum. Let me illustrate it at yet another level. Let us say that we are looking at this particular value of alpha, and here you can now once again clearly see that as the temperature is increasing, the reaction rates are increasing, but then after some point the reaction rates are decreasing and eventually the reaction rates are going to 0. Now, why is this happening for exothermic reaction? Mathematically, we can see this in this particular relationship. Now, according to our discussion earlier, EF minus EB is delta H, the heat of reaction, and this is negative. That means, EF is less than EB. So, in this particular relationship, EF is less than EB, but initially RF is higher than RB, and so the del R del T is positive as a result of this combination. So, in this particular region, del R del T is positive, but what will happen? Remember, our reaction is a reversible reaction of this kind. So, initially the rate of A1 going to A2 is high, but as time progresses, as more of that is as reaction progresses, A1 is going to go down, and therefore, the rate of forward reaction will go down and the rate of backward reaction will come up. So, now EF is less than EB irrespective of where we are, but RF, which was initially higher than RB, is now decreasing as the reaction is progressing. As a result, there is a region where RF EF will be much less than RB EB, or in other words, del R del T will be negative. Now, the transition from del R del T positive to del R del T negative cannot happen abruptly. So, there is a point such as this point, this particular point, where del R del T is 0, and what we see, this white line over here is a tracing of all such points by repeating the same exercise. That is, you take this particular temperature, rate increases, reaches maximum, starts decreasing. So, del R del T equal to 0. So, this is why now if we look at these contours, what we see, these contours are no longer monotonic as they were before. That is, R equal to C is obtained by a non-monotonic, the contour is non-monotonic now, it increases then decreases. Similarly, at all different contours. So, what we have here is very interesting behavior, that the rate increases initially, reaches a maximum value, but then it starts decreasing. Now, qualitatively, why is this happening? Once again, mathematically we saw why it is happening. Qualitatively, it is for the following reason. See, if you look at this reaction A1 going to A2, a reversible reaction, initially there is lot of A1. So, the forward reaction is happening at a faster rate compared to backward reaction rate, and as we increase the temperature, the rate constants are increasing. So, for a while the forward rate reaction increases significantly in comparison to reverse, and we have increase in rate of reaction. However, there comes a point, remember this is a exothermic reaction which determines that as temperature is increased, the rate of the equilibrium extent of reaction decreases. As a result, after certain increase in temperature, the thermodynamic constraints come into picture, because now the equilibrium extent of reaction is limited when temperatures are high, and therefore, the rate starts decreasing and eventually reaching a 0 value, that is this equilibrium line. So, this is the conflict between kinetics and thermodynamics, which is represented in this contour plot. Kinetics wise, temperature increases tend to increase the rate of reaction, but thermodynamic point of view, for a exothermic reaction, increase in temperature tends to decrease the equilibrium constant, therefore decrease the equilibrium extent of reaction, therefore decrease the rate of reaction. And the net result is, for a while temperature has a positive influence, but beyond certain threshold, temperature starts actually limiting the reaction, and this is true for exothermic reaction, whereas for endothermic reactions there is no such conflict. Both kinetics and thermodynamics are favorably affected by increase in temperature, and hence we see these monotonic contours or contours which are always increasing in value. So, with this I want you to keep this information in back of your mind, because when it comes to design of reactors, we will once again visit this to see how our reactor design for exothermic reactions is influenced by this kind of behavior. So, to summarize, we saw how do we define the rate of reaction. For a closed isothermal constant pressure system, we define the rate of reaction as the rate of change of extent of reaction normalized by the volume of the reacting mixture if it is a homogeneous reaction. If it is a heterogeneous reaction, we have several choices, such as for catalytic reactions we do it by normalizing with respect to the weight of the catalyst. Then we have power law kinetics, QJs, QJ primes for forward reaction, backward reaction, order of reaction, overall order of reaction. The rate constant K, the simplest manner in which its dependence on temperature is expressed is a Arrhenius rate expression, K equal to A e raised to minus E by RT, where E is the activation energy. Law of mass action kinetics is a specific case of power law kinetics, where the orders Q's are related to stoichiometry through an appropriate relationship. And finally, we saw how the rate of reaction changes as alpha and temperature changes, that is the extent of reaction and temperature varies. Once again I emphasize that what we saw this variation was for if we assume alpha and temperature can vary independently. We will now bring in the mole balances or design equations for reactors, which will lead us to how this alpha and temperature varies, and this will be the topic of discussion for remaining of this session, that is design equations for reactors. And we will naturally start to begin with ideal reactors and then look at some of the deviations from this behavior at some time in future. So, let us now focus on how the rate of reaction, or how do we design the reactors for by considering the mole balances. So, we are still reviewing undergraduate material, and I should caution you when I say review, some of this material you may not have seen in this particular form, but surely you have seen it in some form or the other. Okay. So, design equations for reactors. We are going to consider ideal reactors and consider the mass balances, and we will follow up this discussion by comparing different kinds of ideal reactors to see how we choose a reactor for certain processes. So, what we are going to do to begin with is write a simple mole balance for the reacting species, and once again we are going to say that we have n species A1, A2, n such species A n, in which this reaction nu j A j equal to 0 is taking place. But this reaction is now taking place not in a closed system, but in an open system. So, we have this reactor, we do not know what this reactor is, but there is some reactor in which this reaction is taking place, and as I said, this is an open system. So, there is a flow coming to the system and flow leaving the system. So, there is an entry point and there is an exit point for material to flow in and out of the reactor. Now, before we go to our mass balances, few comments about the notation that we are going to follow, so that we are all clear about what are the different terms we are talking about. To begin with, capital F is the molar flow rate, moles per minute, and we put subscript j to denote that we are writing molar flow rate of species G species J, and additional subscript O for denoting the entry point of the reactor. So, Fj0 for example is the molar flow rate of species J that is coming into the reactor. Fj is which is going out of the reactor. Then small v is the volumetric flow rate. What we talked about is the molar flow rate, moles per minute. Now, we are talking about volumes per minute. So, let us say dm cube per minute, and again V0 that is incoming, V that is outgoing. That means, at the entry point V0, exit point V. We have something happening in the reactor. What is that? Of course, the reaction. So, there is a rate at which this species J is undergoing a change, and let us write its rate as Gj, and G to denote that we will call rate of generation, molar generation rate, and again it is in moles per minute. V, capital V is the volume of this reactor, capital V is the volume of this reactor in which this reaction is taking place. Again, when I say volume, it is a volume of the reacting mixture, which could be 70%, 80% of the reactor volume, but that is how we understand the concept of volume. Cj is the concentrations, moles per volume unit. So, it is nothing but the ratios of corresponding capital F and small f, and T is the time, let us say. Let us do a general mole balance and see how we get this particular mole balance. So, let us do this balance for a small volume, so that we follow the steps that are involved. So, let me emphasize again, this is my reactor, the rate of generation is Gj, whatever is coming is Fj0, whatever is going out is Fj, okay. And we are clear as of whatever different terms that we are going to use. One more term that we are going to use is Nj, which is the moles. So, this is in moles, mass, okay. So, now we do a simple regular mass balance, mass in minus mass out plus generated must be what is accumulated in the reactor. That is our standard typical mass balance for any process. Chemical reactions is no exception. In, out, minus out plus generated equal to whatever is accumulated. Okay. Let us say that we do this mass balance over a small time step delta t. So, in time delta t, how much is the mass that has come inside the system? If Fj0 is the molar flow rate, moles per minute, then Fj0 into delta t must be the mass of J that is coming in the reactor. What is the mass that is going out of the reactor? It is Fj. So, during same time interval delta t, Fj must be the mass that has left the reactor or the system. How much was generated? Gj times delta t. Gj is the rate of generation in the reactor. So, in time delta t, Gj into delta t must be the moles. Note that all these individual units are in moles, okay, moles of species J. And how much would have accumulated inside the reactor? Accumulation inside the reactor is Nj at time t plus delta t minus Nj at time t. That is all we are saying is this were the moles at time t plus delta t, and if this were the moles at time t, then in time interval delta t, this difference is how much has accumulated in the reactor. Now, if we divide the whole both sides by delta t and take limits as delta t goes to 0, we get our mass balance equation Fj minus Fj0 minus Fj plus Gj is d dt of Nj. Since we are dividing this mass balance by delta t, what we have is the now expression in terms of rates. Each of these unit has, each of these term has a dimension of rate now. The left hand side, or let us start with right hand side. Right hand side is the rate of accumulation of species J, dNj dt, which is the result of what is coming in Fj0 minus Fj what is going out, and Gj the generation rate into that must be the accumulation, the net rate of accumulation. Now, we know what is inlet, outlet and so on. Let us spend some few minutes on what is this generation rate. Okay. Now, generation rate, we said that it is in moles per minute. If we for example assume that the working conditions are such that there is no variation inside the reactor, variation of temperature or concentration or any quantity that influences the rate of reaction. That is, temperature is uniform all throughout, concentrations are uniform all throughout, and you would have by now guessed we are now talking of perfectly mixed reactor, a reactor in which there is very good stirring, so that there is no variation within the reactor. To put it formally, there is no spatial variation of concentrations, temperature or any other quantity that influences the rate of reaction. If that is the case, then our earlier definition of rate of reaction R j, what were its units? Its units were moles per dm cube per minute, let us say, the rate of generation of species J. Recall that R j is nu j into R, where R is the rate of reaction. I keep repeating this thing because I believe certain degree of repetition does not harm anybody. So, we have R j as the rate at which the species J is undergoing reaction, and it is same throughout the entire volume. If that is the case, then R j multiplied by the volume of the reactor must be the rate of generation, the total rate of generation of species J, that is G j. So, if there are no spatial variations, then we have this particular G j, which is R j into V. Okay. So, that is the balance. So, now let us go back to our mole balance, and let's go back to okay, let's go back to this particular expression before we actually move to looking at the set of equation. Now, this is what we said is the case when there is no spatial variation, but let us say that there is a spatial variation. Okay. That is, things are not uniform in this reactor. So, what we can do is consider small volume elements delta V1, delta V2, delta V3. So, these are all small volume elements delta V, and in this volume element, let us say Vk, Rk is the rate of reaction, Rk is the rate of reaction. So, in this volume element K, delta Vk delta Rk, or rather Rk into delta Vk must be the rate of generation in this volume, but there are so many other elements. So, we can add up all the contributions from all these small volume elements. So, let us say that summation Rk delta Vk over the entire set of volume elements, small volume elements, this must be now my generation rate G j. So, what we are saying is that we are now looking at this system consisting of small volumes delta V in which things are uniform. Okay. This is just for argument's sake, and contribution to the net rate of generation of species J is coming from each of these small volumes, and each of these small volume has a contribution Rk into delta Vk, where Rk is the rate in that particular element and delta Vk Rj, let me write this once again, Rj is the rate in that particular volume element times delta Vk. So, we can write this as Rjk, that is the rate of generation of species J in the element K and the volume of that element, and summed over all this K. Now, once again we can make these volume elements smaller and smaller and smaller, such that delta V k tends to 0, then summation of series is converted into integral, and what we have is G j is integral R j dV, that is summed over or integral over the entire volume V is my net rate of generation. So, now let us go back, and this is what is that mole balance that we get, that is F j 0 minus F j plus integral R j dV is d n j dt. Once again, molar flow rates, the intrinsic rate of reaction or intrinsic rate of species variation R j per unit volume times dV summed over the entire volume is the rate of accumulation. Let us now simplify these mass balances for various different scenarios. So, going back, our mass balance, general mass balance equation is this. Let us consider a batch reactor. In a batch reactor, we know that there is no inflow, there is no outflow. That means, both these terms disappear, and stirred tank reactor operated in a batch mode. So, conditions are uniform throughout the entire reactor, and we have d n j dt as R j into V as our mole balance. Straightforward exercise. Let us see what happens for a continuous stirred tank reactor operating at steady state. That means, when steady state is reached. So, once again we have we are doing a steady state balance, and for a stirred tank reactor where there is a material coming in, material going out at these rates F j 0 and F j at steady state. So, this is 0, we are left with F j minus F j 0 minus F j as minus integral R j dV, but once again we have uniform conditions in the reactor. So, this is nothing but R j into V, and we have our mass balance equation for a stirred tank reactor, V equal to F j 0 minus F j by minus R j. What happens for a plug flow reactor? There are various ways of looking at it, but let us go back to our generalized mass balance equation d n j dt as F j 0 minus F j plus integral R j dV. Recall, for a plug flow reactor, the fluid moves into the reactor like a plug. So, one part comes in, then we have entry of next part, it pushes the part further, and there is a continuous movement. There is no mixing or communication between the fluid elements which are in the reactor. So, it is just like a plug. So, we can simplify this mass balance equation at steady state. This is 0, and we have F j 0 minus F j, which is minus integral R j dV, and we can differentiate this with respect to V and express this thing as d dV of f j, d dV of this whole quantity, f j 0 is fixed. So, d dV of f j is nothing but or rather minus R j or d f j dV equal to R j. This is our mass balance equation for a plug flow reactor. We will stop here and then continue this discussion by looking at how do we compare the performances of stirred tank reactor and plug flow reactor in our next session. Thank you.